Good afternoon, class. We are looking at pre-calculus practice test number 2, module 2, covering chapters 3 and 4. And here's chapter 4, exponential and logarithmic functions. Here's the first one. Find the formula for an exponential function that passes through points 0, 2000, 2, 20, and f of x is a, b to the power of x. All right, so basically you just plug it. You plug in this pair into this function by representing x with 0 and the y or f of x with 2000, the same thing with the second. So when you plug in the first one, 0, 2000, you get f of 0 is a, b to the power of 0 is 2000. When you plug in the second one, 220, you get f of 2 is a, b squared equals 2. So this is 1 and a becomes 2000. So we can replace the a with 2000. So f of x becomes 2000 b to the power of x on the one hand. On the other hand, f of 2 is ab squared. So that means 2000 b squared. And now solve for the missing b. To do that, we are going to divide both sides by 2000. And we get 1 over 100. And b has two answers. When b squared is 1 over 100, b is 1 over 10 or negative 1 over 10. We can only have a positive base. As you recall, when we write exponential functions, we make sure the base is positive, because this way it becomes a one-to-one function and it has an inverse. All right, so let's deposit this much, $10,250 into an account that earns 4% compounded interest. And I'm reminding you the formula A of t is P times 1 plus R over N to the power of NT. How much will the account have at the end of 10 years if it's compounded monthly? So what we are looking at is that the P or principal is $10,250, or the rate is 4% or 0.04. T is 10 years. And N, in the case of a monthly, N is the number of compounding takes place per year. So annually, N would be 1. Monthly, N would be 12. So we plug in 10,250 times 1 plus 0.04 over N times T. And for this case, N is 12. Divide 0.04 by 12, add 1. This is 120 raised to the power of 120, multiplied by $10,250, and it gives you the total of $15,281.03. By the way, when it comes to money, we go with 2 decimals. That means we go to the third one and we make a decision. How much will the account have at the end of 10 years if it's compounded weekly? So everything is the same here except N is 52, everybody. So we plug in all the values, and for n, we put 52. We put that into a calculator, and it gives us a little bit more, $15,288.85. And as I've mentioned before, when it comes to money, you go to the third decimal to make a decision here. That's how you do the rounding. How much will the account have at the end of 10 years if it is compounded continuously? As you recall, the formula would be A of t equals PE to the power of RT. So we plug in everything that we have. P, $10,250. Remember, E is about roughly 2.718, and it continues indefinitely. R is 0.04. And T, in this case, is, of course, 10 years as before. So you plug it in, 10,250 times e to the power 0.04 times 10. This is simply 0.4, e to the power of 0.4 times $10,250. And that's a little bit more than that. Gives us $15,291.20. What is the doubling time for this formula? In general, A of t equals P e to the power t. In general, when we say double, that means the amount will be 2 times the amount we begin with, which is P, or the principal. So to calculate that, I want to go over that in general by replacing A with 2P, because that's the concept of doubling. Because half-life also, when something decays, you can discuss the half-life, the amount of time it takes for it to go to half of its size. Doubling means to go to double of its size. Conceptually, they are very straightforward, and this is how you calculate them. So in this case, P on both sides drop, and you get 2 eta equals e to the power of RT. You are going to take the natural log of both sides. So the left side is ln2, and the right side is simply RT. Now, from here, you can find the T to be ln2 over R. By the way, sometimes we may be interested in calculating the R. Okay, that becomes ln2 divided by 2. So this is the general formula. We proved it, and now we are going to say T equals ln2 divided by R, which is 0.04. Putting it into a calculator results in 17.3868. As far as how many decimals normally they tell you, and then you make a decision. If they don't tell you how many decimals, go with as many numbers, as many decimals as possible. Here's the graphs given. Use the graphs shown to answer the following questions. All have the form f of x equals a, b to the power of x. Which graph has the largest value for b? Which graph has the smallest value for b? So in general, to give you an idea, okay, when you look at exponential functions, in the case of an exponential growth, the larger the base, the closer to the y-axis, okay? And in the case of a decay, the smallest one, the closest to the y-axis from the left. So let's remind everybody, when you graph y equals a to the power of x or b to the power of x. When a is larger than 1, we are talking about exponential growth. When a is between 0 and 1, it's an exponential decay. A simple example, if we compare f of x equals 2 to the power of x versus h of x is 2 to the power of minus x, you see that this is an exponential growth and this is an exponential decay. Another way of writing this, I want to make sure we understand this. We could think of this as 1/2 to the power of x. That's referring to the base being between 0 and 1. Okay. Now, of course, when we say 0.5 or 1/2 is the same, this is 2, this is 1/2, okay? And if you compare these two, you see the larger the base, this is 2 to the power of x, this is 5 to the power of x. The larger the base, the closer the graph to the y-axis, meaning it rises faster. Also, if you look at y equals a b to the power of x, it's showing that this one, the y-intercept is 0, 1 here, and the y-intercept here is 0, a. Because over here, the number in front of a is nothing, which means 1. In this case, the number is a. So again, this is just to give us an idea how the graph works, so it will help us with the answering. So which graph has the largest value for b? First of all, it has to be on the right side. Okay, one of these. And the one, again, compare this to the one that is closer to the y-axis. Closest to the y-axis on the right. That makes the graph of d. Which one has the smallest value? Okay. Now this time is closest to the y-axis, but from the left. So those, which one is the closest? The green one, C. Which graph has the largest value for A? Which graph has the smallest value for A? Remember, the y-coordinate here is 0, 1. The y-coordinate here is 0, A. So you want the largest A. You want the largest y-coordinate for the y-intercept. So in general, we said it's 0a when the base is b, but this is the number in front is a. So largest a or the y-intercept would be this point for the graph of the green one, the graph of C. Now look at this one, this one, this one, this one. Largest, smallest. Smallest is this one, which belongs to the last one, curve or graph F. Use transformation of the graph of f of x equals to the power of x of the function below. State the horizontal asymptote, the domain, and the range. When y equals 2 to the power of x, it looks like that. Again, 2 to the power of x, 3 to the power of x, 5 to the power of x. When the base is larger than 1, looks like that. I hope you remember it from the previous page. So the y-intercept is located at 0, 1. So if we look at this graph, reflected with respect WRT with respect to. it flips over this way, gives you y equals 2 to the power minus x with the same y intercept of 0, 1. So the difference is, see, they have the same domain. They have the same domain is all real numbers. They have the same range from 0 to infinity. They have the same y-intercept 0, 1. Okay. And this one is increasing, but this one is decreasing. And by the way, they have the same horizontal asymptote, which is the x-axis or y equal to 0. So f of x is 2 to the power minus x. Horizontal asymptote y equal to 0. Domain is all real numbers. Range is from 0 to infinity. What about g of x equals 2 to the power of x plus 1? Then we go back to this one, a basic function. And we are going to shift it up by this much, by 1 unit. So shift this up by 1 unit. So as we do that, a couple of things happen. So y equals 2 to the power of x plus 1. Here's the horizontal asymptote, which was the x-axis, or y equal to 0, shifts up by 1 unit. And the y-intercept of 0, 1 shifts up by 1 unit as well. So horizontal asymptote y equals 1. The old y-intercept and now the new y-intercept look at 0, 2, which means this is going to have the same domain, but the range goes from 1 to infinity. Of course, 1 is not included. The horizontal asymptote was y equal to 0, but now it's y equals to 1. So for this function, f of x equals to the power of x plus 1, horizontal asymptote y equals 1, domain negative to positive infinity, and range 1 to infinity. Consider the function f of x equals 4 to the power of x with a function that results from the given transformation. So let's figure out what happens here. So we are given the function. We want to shift this 3 units up. So just add 3. Shift f of x. That means go back to the f of x, not this one. Go back to f of x. Shifted 5 units left. So change the x. If it's left, x plus 5. If it's right, x minus 5. Because it's left, change the x to x plus 5. So h of x is 4 to the power of x plus 5. Reflect f of x. Again, go back to f of x. About the x-axis. So put a negative sign in front of that. Reflect f of x about the y-axis. So go back to the function and change the x to minus x. So that's pretty straightforward, everybody. The graph below is a transformation of f of x equals 2 to the power of x. So f of x, which is 2 to the power of x, has been shifted in perhaps so many ways to get here. Write an equation of the graph shown. Couple of things you want to notice is the y-intercept at 0, 2, and we have the horizontal asymptote y equals 3. So these are the things we notice. Now let's go back to the function 2 to the power of x. Looks like that. The horizontal asymptote is the x-axis for y equal to 0, and the y-intercept is at 0, 1. So we notice the transformation as follows. G of x is minus 2 to the power of x, okay? Because this seems to be flipping over. If you look at this one, seems to be flipping over. So reflected across the x-axis, and you get this one, which means we have still the same horizontal asymptote, but the y-intercept is changed to 0, -1 now, but the same horizontal asymptote. Now look at this one. The horizontal asymptote is y equals 0, but it goes to y equals 3, and that tells us that it shifts up by 3 units. Shifts up by 3 units. Y equals 0 becomes y equals 3. So that should be very obvious as to what's going on, I hope. This is located at 0, 2. H of x is negative 2 to the power of x plus 3 as a result. So you can look at this graph or this one. That's the final function. Logs, if b is larger than 0 and can't be 1, y equals log x base b is equivalent to x equals b to the power of y. So x equals b to the power of y is the same as y equals log x base b. Conceptually, this is the exponential format, this is the logarithmic format. Notice they have the same exponent and the same base. So if you look at what I'm going to do here, look at this arrow and follow the arrow b to the power of y equals x. So if you can go from one format to the next easily, you have no problem with logs. In general case, when y equals log x base b, b to the power of y equals x, and we have the following properties. And some of them are easy to see just with this arrow. Okay. And these two, what do they refer to? So log 1 with any base is 0, log b base b equals 1. When the base and the argument are the same, this is called the argument. So this is called x is the argument, okay? Let me just write that, just make sure we argue. argument of log. And so with that being the case, if they have the same base and argument, becomes 1 b to the power of x b. And these two, if you look at this one, log base b of b to the power of x is x, or b to the power of log x base b equal to x. What it means, logarithmic functions and exponential functions are inverse functions. Log xy base b is log x base b plus log y base b. This is the product rule, the quotient rule, the power rule. If we go to common log, log x base 10, we don't write the base. That means the base is 10. 10 to the power of y becomes x. And we should be able to make this transition easily. So let me quickly look at a couple of them. This one, first of all, you drop all the bases b. That's as far. So I hope you see that 5, 6, 7, and 1 become obvious. Just drop the base b. That's all. Number 1, number 5, number 6, number 7. What about number 2? Number 2 says the base and the argument must be the same. When you don't have a base, the base must be 10. Number 3 says log base b of b to the power of x. Well, 10 to the power of x, you know the base is 10. And this one, again, we know the base is 10. So I hope you can make this transition. As also, in this case, when we write ln, we mean log x base e. Please don't write that, okay? Please don't write that. That you have to use y equals ln x, which means e to the power of y is x. And so what happens, first and foremost, log changes to ln for all of them, then there is no base. So number 1, 5, 6, 7 are obvious, just you're changing them to ln. Number 2, these two must be the same. So the moment you write ln, you know the base is e, so ln e equals 1. This one, the same thing, ln, so it must be e to the power of x. And this one, b, the base is e to the power of ln x equals x. You have to be very comfortable with these properties to have an easy time understanding logs. So we really have to study this and get very comfortable with it. Of course, you can find it proof in the lecture. Now, logarithmic functions and exponential functions are inverse functions. For example, y equals ln x and y equals e to the power of x are inverse functions, and they are symmetric, therefore, with the line y equals x. And this is called the change of base formula. Log x base b is log x over log b with any base, for example, a. However, that's really not usable. You use the common log or you use the natural log for the sake of calculation. Also, if you do the cross product, here, multiply these two, you get this one. So log base b of a times log x base b, so you can put log x base a if these two are the same, okay? And it can continue actually indefinitely. If the base, in this case, the argument is equal to base, and you continue with the next one, you can write. Also, notice that when x is between 0 and 1, ln x is negative. When x is 1, ln x is 0. The rest of it, when x is larger than 1, ln x is positive. So that would be helpful to know. We want to rewrite each equation in exponential form. again, reminding everybody that y equals log x space b means b to the power of y equals x. Y equals ln x means e to the power of y equals x. Y equals log x means 10 to the power of y equals x. So we should know when the base with log is missing, the base is 10. That's why you really shouldn't put that there. By now, you should know that. All right. So with that being the case, let's look at this one. 5 to the power of q is m, just by definition. In this case, we write it in this format. And remember, ln, we are supposed to know the base is e. So e to the power of z is v. Same thing here. We don't write the base is 10 because we have log. So 10 to the power of t must be w. Going back from logarithmic format to from exponential format to logarithmic format. So log of the result, which is y, the same base, 3 must be x. Log y base 3 equals to x. The moment you see e, you're going to use natural log. Natural log of the result, h, is the exponent, k. Log base 100 of the result, which is b. So log base 100 of b is the exponent, a. So I hope everybody can go back and forth, having no problem with this area. State the domain, vertical asymptote, and the end behavior of the function f of x equals log of x minus 7. So we know the graph of y equals log x looks similar to that with the just the information would be the domain is from 0 to infinity. The range is from negative to positive infinity. The x-intercept of 1, 0. There is no y-intercept. And now we have a vertical asymptote, which is the y-axis or x equals 0. So that's for log x. By the way, as far as the domain and the vertical asymptote, quickly, if you set this equal to 0, that becomes the vertical asymptote, x equals 7. And this argument must always be positive. So x minus 7 larger than 0, that would be the domain. So you know how you find that. But in any event, log of x, so this, of course, as was mentioned, 1, 0. Now, x minus 7 shifts to the right by 7 units. So this point, which has coordinates 1, 0, now goes to the point with coordinates 8, 0. And that's the vertical asymptote. So as I mentioned here, you set this one equal to 0, you get x equals 7 as the vertical asymptote. Okay. So just in case. And the domain is everything to the right of this. 7 to infinity, but it doesn't change the range. Domain is 7 to infinity. Range is negative to positive infinity. And as far as the end behavior is concerned, of course, I hope you see that as x goes to infinity, y goes to infinity. As x goes towards 7 from the right, of course, f of x goes to negative infinity. So it's important to know. Later on, we look at this notation in calculus. This is 7. This means 7 from the right. If I put a negative sign, means 7 from the left. So 7 from the right, like for example, 7.1. 7 from the left, like 6.9, just to give you an idea what it means. Okay. We state the domain, vertical asymptote, and the end behavior of this function. Not the same question, but a different function. G of x is ln of 2 minus x. So we start with y or f of x equals ln x. That's the elementary function. We should know the graph. The graph looks like that. In general, y equals log x, okay, when the base is larger than 1, looks like this. Like log x when the base is 10, or log x when the base is 2, or anything like that. So we can see what's going on. A couple of things I want to mention. Obviously, we have the y-intercept located at this point, which is 1, 0. The domain from 0 to infinity. The range is all real numbers. And the y-axis is the vertical asymptote. So this point has coordinates 1, 0. Now what happens to this function? We start with ln of minus x by changing x to minus x. We flip this over with respect to the y-axis. So reflect this one across the y-axis to get this one. So this is y equals ln of minus x. Okay, so from here, we get to the function y equals ln of minus x. All right. Now this point, which was located at 1, 0, the x-intercept moves to this point with coordinates negative 1, 0. Now, minus the parentheses x minus 2. I hope you recognize this as equal to 2 minus x. But this will give us that this function, okay, has been shifted 2 units to the right. Shift right by 2 units. Shift right by 2 units. So we had this function, then we had the green one, and now the green one has shifted to the right by 2 units. We originally had the x-intercept at 1, 0, a negative 1, 0, and now it has been shifted back to 1, 0. So this one has gone back to 1, 0 because you add 2 to this number, comes 1, 0. So this new function has the same x-intercept as the original. And so we also notice this line, which is the vertical asymptote. In other words, set this one equal to 0, 2 minus x equal to 0. You just set the argument equal to 0, and it gives you the vertical asymptote x equals to. So what's happening now? The range hasn't changed, all real numbers, but the domain from negative infinity and stops at 2, so from negative infinity to 2, and the end behavior is that as x goes to negative infinity, so does y, but as x goes to 2, then y goes to negative infinity, and it's very important. So domain from negative infinity to 2, range, all real numbers, and behavior. As x goes to negative infinity, so does y, but as x goes to 2, g of x goes to negative infinity. Please understand, as you look at this graph, is from the left of negative 2, so x approaching of 2. X approaches 2 from the left. This means like 1.9. Okay, 1.999. That's the concept. Okay. All right. State the domain, vertical asymptote, and the end behavior of the function h of x equals minus log of 3x minus 4 plus 3. Well, again, we start with the basic function y equals log x, which looks like this with the x-intercept of 1, 0. Again, domain from 0 to infinity. Range, negative to positive infinity. X-intercept at 1, 0. There is no y-intercept, and it has a vertical asymptote, which is the y-axis, or x equal to 0. So as we look at this one, we notice this number 3, although we have to take it out. We take it out in a moment, but we notice number 3, which means it's a horizontal shrinkage by a factor of 3, meaning this function, which has the, it shrinks along the x-axis, which means has the x-intercept at 1, 0. Now it goes to 1/3 0. So this is the one that we had. Now the new one has a location 1/3, comma 0. That's important to understand everything. Now, when we go back to this, if we take the 3 out, just look at this part, this part. Never mind the rest of it. If you take the 3 out, you get 3 times x minus 4/3. So you have log x, you have log 3x. Now what happens is that this is shifting to the right by this much, 4/3. So we are going to shift this one to the right by 4/3, resulting in this red graph, and 1/3, 0 goes to this point, which means you are going to add 4/3 to this and you get 5/3. So the new x-intercept has a location of 1/3 plus 4/3. So that's how you get the 5/3. You add these two numbers. To get 5. Okay, so we are here. Now the next thing we note, so by the way, this is identical to that. This one, let me, this is identical to that. But now we see a negative sign in front of it. And we're going to apply that. When you put a negative in front of that, means you are flipping it over with respect to the x-axis. So this last graph that you have, flip it over, reflected across the x-axis, and it will look like this now. So now we've got everything up to here. What is missing? +3. What do we do? This last graph, we shifted up by 3 units. So this one is located at 5/30. Okay, this hasn't changed. Just flipped over. Look at the red one versus sort of the bluish color. And now we are going to move this up by 3 units. And that would be this function, of course, which is the same, okay? This is the function. And when you move this, this old x-intercept, this x-intercept shifts up by 3, which means the x-coordinate is 5/3, but the y-coordinate is 3 now. So this point has been shifted up here with the coordinates 5/3, 3. Now, let's explain everything. So first and foremost, this function is the same as this one. And we did this transformation for the sake of being able to graph this accordingly. So first, that's the same function, y or h of x, okay? You can call it h of x, okay? It doesn't make any difference. So y or h of x, it's the same in any event. Now, what happens is that now when you set this one equal to 0 or this one equal to 0 makes no difference. Clearly, that says the vertical asymptote x equals 4/3. This is the graph of the function. This is the point with coordinates 5/3, 3. Okay. This is the vertical asymptote, and it has the equation x equals 4/3. If you set 3x minus 4 equal to 0, or this one makes no difference. The vertical asymptote x equals 4/3, which means, as you can see from the graph, the domain is starting from 4/3 and goes to infinity. Of course, 4/3 is not included. Range, there is no change, all real numbers. The end behavior, as x goes to infinity, y or h of x goes to negative infinity. As x goes to 4/3, h of x goes to positive infinity. And more specifically, 4/3 from the right. There, let's write it. Domain from the vertical asymptote, 4/3 to infinity, 4/3 is not included, everybody. 4/3 is not included. That's why you put parentheses. Range, all real numbers. The end behavior. When x goes towards 4/3, towards the vertical asymptote, h goes up to infinity. As x goes to infinity, h of x goes down to negative infinity. And again, I want to make sure everybody understands it's really 4/3 from the right side of 4/3, okay? Because from the left side, the function is not even defined. And that's what happens in calculus. I want you to be familiar with notations as we come across them, everybody.